So last time we learned how to calculate pressures on walls, and now we're going to turn those pressures into forces. So the pressures come from soil, and there's the at-rest condition, there's the active condition, there's the passive condition, and we talked about non-cohesive materials and cohesive. So non-cohesive meaning something like sand or gravel, a granular type material. So to start this off, let's do a quick fluid mechanics review. So let's say that we've got a wall, and it's going to hold back just water. And let's say that the height of the water is 7 feet. And we want to know what is the resultant force that's acting on the wall. So in fluids, we probably drew a triangular pressure distribution and described the force of the water this way. And if we wanted to know what is the pressure at any point, but in this case particularly at the bottom, P would be, the pressure would be gamma times H. And so for water, gamma is the unit weight, and for water that's 62.4 pounds per cubic foot. So if we wanted to calculate the pressure at the base of the wall, it would be 7 feet times 62.4. That's 436.8 pounds per foot squared, or PSF. All right, so that's the pressure. We did that last time. Now we've got to figure out what is the force or the resultant from that pressure distribution and where does it act. So what we want to think about is the center of pressure. And for a triangular distribution on a wall, we're going to analyze the wall on a 1 foot basis. So there's not a potato-shaped gate or a circular gate or something like that. It's a slice of wall that's 1 foot thick or 1 meter thick, depending on what unit we're in. So that's going to be, the center of pressure is going to be at the 1/3 mark from the base of the wall. And if we wanted to calculate that, it's just the area of the triangle, that triangular distribution. So that's 1/2 times the base, which is pressure, times the height. Now we can talk about the pressure. Remember, the pressure is just gamma H. And so another way that we could write this thing is 1/2 gamma H squared. But if we use the original way that I wrote it, then it would be 1/2 times 436.8 PSF times 7 feet, and that's 3,058 pounds per foot length of wall. So if we had a 10 foot length of wall, it would be 30,000, but we're just going to analyze this on a per unit length basis for all of the problems. And so it's going to be this same approach, but now we need to use soil pressure that we learned to calculate last time instead of water pressure. And so here's an example for at rest. So at rest is a condition where the wall's not allowed to move at all. And so the first thing that we want to take a look at is what is the horizontal pressure at the bottom of the wall. And you're going to see some larger equations, and I'll tell you my preference is that we calculate that horizontal pressure at the base of the wall first, and then just multiply that to get the area of the triangle. So 1/2 times that value times the height of the wall. And so in order to get this value, we need to calculate what's the vertical pressure or vertical stress on the soil at the base of the wall. So if we're imagining a unit of soil there, we're interested in knowing what's this pressure, sigma prime sub v. And it's got to be prime. And so, hopefully from soil mechanics, we remember how to calculate vertical pressure. It's just the total stress minus the excess, or minus the pore pressure. And you see that calculation play out here. And it even shows you how to calculate the force for water pressure also. So we just went through this example. So once we get this value calculated, we can get the horizontal stress calculated, and it turns out that the horizontal stress, or the resultant force, breaks down in a very similar way to what it did for the water calculation. So this thing right here is kind of like the unit weight of water in the previous example. So you can do it this way, but if it were me doing the calculations for P naught prime, so the naught means at rest, the prime means that it's effective stress, and so I would do this calculation 1/2 sigma prime h for horizontal times the height of the wall. And that's nice because now we've got this thing. It's a little bit easier calculation. It's a shorter step, and we might need to know that value. It might be helpful to have that value. So that was the at-rest condition. This is the active condition. So now, and this is for a granular material. So we're going to go through the active condition for a soil with cohesion like a clay. So the idea is the wall's got to move away by some amount. Last time we talked about how far it would need to move. It's not insignificant, but it's not very far either. So it's not like this thing's sliding down the hill to get this to work. So again, what we need to do is we need to calculate the pressure. At the bottom. And so here they're calling this the active pressure. So we're going to calculate that. And the way that we get that is by calculating the vertical stress, effective stress, and then multiplying it by the value of K active. So to get K active, we use this equation. And we went through how to get this. These are effective friction angles. We went through how to get this based on Moore's circle last time. So how about passive forces? It's sort of the reverse of the last. So we need to have the wall move towards the backfill material, and the horizontal stresses increase and increase and increase until the soil starts to fail. So again, we would have a triangular pressure distribution, and we need to know this magnitude. This time we're going to multiply it by K passive, and K passive is this equation. This is all going to come together in a slide later. So what about for cohesive material? For cohesive material, it's just a different type of a failure. So we're going to use total stress analysis instead of effective stress analysis. And so we want to review real quickly why that is. Basically, there's not time to allow volume change, and if there isn't going to be volume change, then there can't be an increase or decrease in strength based on changes in stress. And so no matter what happens, the soil strength is essentially fixed. So what that means is as the horizontal at-rest stress reduces as the wall's moving away, the Mohr circle reduces the horizontal stress until failure is reached. And at that point, this soil will start to fail. So again, we'll do the calculations again to try and find the base of the triangle. And we don't want to build walls out of clay, so it's okay. We don't really want to use clay, so we won't spend as much time on this. So we'll get this value of K active, and then we'll run the calculations like this. So what you can see is we end up with, if this is sort of 0 on a stress axis, and so everything to the left is tension and everything to the right is compression, and that's a little bit easier to see right here. What ends up happening is we get a tension component in the wall face. So as this wall is trying to move away, there's actually a suction force that's described right here that's sort of holding the wall from moving. And it turns out also that this is the depth that a tension crack could form in a situation with clay. So in theory, this clay could stand on its own, self-supporting, as long as the wall height was less than this value. But we don't want to count on something that has a suction force or a tension force, because the likelihood that that thing might be breached by an air pocket, so air intrusion comes in and that thing opens up a crack and now all of a sudden that tension goes to 0, is not that unlikely. And so instead of doing that, what we ought to do is discount this component. Take that triangle out. So not all books show this. So oftentimes you'll actually see this as the value that's being reported for calculating the resultant active force. And so the way that this works is there's a horizontal resultant here that is acting in tension, that's actually trying to hold the wall up, and then there's a horizontal resultant that's acting here that's trying to push the wall over. And if you do the subtraction on those two, this is the equation. But if we discount the component up here, then what we end up with is an equation that looks like that. And that's the one that we should be using, because it's a conservative value, and it takes into consideration the possibility of a tension crack opening up as opposed to a suction force. For passive conditions, it's a little bit simpler. There's not this conservative thing that needs to happen. So we start with the at-rest horizontal stress, and as the wall is being pushed into the backfill, the horizontal stress increases and keeps increasing until the Mohr circle intersects with the failure plane. And at that point, the horizontal stress won't go up anymore. It will start to fail actively. This material will wedge up. And so the equation for what that resultant would be is right here. These are all, you can all derive these pretty easily. It's pretty fast. I mean, the last figure kind of shows you how to do that. So that's all fine, but there are a lot of things that weren't considered in that last setup. So one thing that wasn't considered is, well, what if our wall is retaining soil that has an angle, right? And this is not that unreasonable. What are we to do then? It doesn't take into that doesn't take into consideration this angled wall, but we know that by having more material above the backfill, it's going to increase the likelihood that the wall fails. And what that really means is that there's going to be an increased stress on the back of the wall, right? So this stress is going to go up because of the backfill. And so Rankine's got a theory, and we want to try and use Rankine anytime we can because it's relatively easy to use, and I'll show you the equation here in just a second. We're going to calculate K a little bit differently. But we need to go through what the theory is and what the assumptions are so that if we are not able to follow these assumptions, then we have a problem. So the first thing that, pretty much all of these types of theories are going to say is that the soil is homogeneous. That means it's, uniform, and that it's isotropic. So that means that it doesn't have different strengths in different directions. And then the other thing that they're saying basically is that failure is going to happen along a straight line. Now, this is actually not all that true. Oftentimes the line has a little bit of a curve to it, but that starts to make things a little bit too hard. So we need to say that it is on a straight plane. We're also running this like in a per unit length basis. And so we're saying that the wall is infinitely long, right? And that makes sense. So that's not really that big deal. And then also we're saying that the wall has to be able to move enough to fully develop the active or the passive condition, whichever one it is that we're counting. Okay, and then the last thing, and this is the trick, is that Rankine said that the resultant is going to act, and I should have drawn my arrows inclined. The resultant is going to act inclined along that same angle as the surface of the backfill. And so here's the equation for active. So I called that alpha last time, but that's going to be beta. So the basic setup is that we've got this inclined pressure distribution, and it's inclined by the same angle as the top, and that's only going to work if beta is less than the friction angle, and that's fine because if this was sloped greater than the friction angle, the surface material would probably slide off. So we'll use this equation for calculating the active condition. And first thing this is another reason to go ahead and do the calculations the way I originally showed you with the fluid mechanics pressure example, that we want to calculate this dimension first and then calculate the value of PA second. It's gonna simplify some things. Here's the full equation if you want to skip that step. So that's active. Passive, we're just going to flip some signs. And it's going to work basically the same way. So passive conditions would hold still. If we were to try and go in here with a bulldozer or something like that and push this wall, the resultant is still going to be inclined beta, and it's going to be even higher, right? Because there's even more material that we've got to push up, we got to lift up out of the ground. If beta goes to 0, then we revert back to all the things that I was just showing you. And so all the things that I was just showing you is the only things that I remember seeing on the PE exam. So this Rankine theory, all of the backfill was inclined by the same angle. It was 0. So there was like 3 or 4 problems, maybe even 7 problems that were the same way in the PE. But it's not that realistic. It's very likely that we would have an inclined backfill. And so if that happens, here's one way to do it. Rankine. Now Coulomb has another theory that will allow for an inclined backfill and the back of a wall that's inclined, alpha. So I used the wrong symbol earlier. There's where alpha comes in. And then it also considers that there's going to be wall friction along the back of this facing, which is going to help stabilize the wall. One of the things that we're going to look at is this wall going to want to tip over? And if it does want to tip over, if there's something pushing down on the backside of it, that will stabilize it. And so this is another opportunity to be a little bit more aggressive with design. So it is a much more complicated equation. It is very conducive to programming into Excel so that once you get it set, then you don't have to worry about making an algebra mistake later. Again, beta is going to be less than alpha, so that's the same as last time. So when we're calculating Ka, here's the equation. And so there's several philosophies on this. This is how it was presented to me, the way that I've got it drawn here. I'm going to draw an alternative to it here right now, but let me describe this one first. So basically, here's one equation that describes this particular figure. And so we just solved for the stress that's normal to the back face of the wall. And there's another equation for the stress that is parallel to the back face of the wall, like a shear type of a force. We haven't seen it yet, but we are going to some moments and some forces in the x direction. And so at some point, we're going to want all these forces to be either horizontal or vertical. And so in my opinion, a better approach to what's presented here is to calculate R, the complete magnitude of the resultant. And so R is just going to be 1/2 gamma Ka h squared. And then we've got to recognize that this angle it's going to be inclined by phi wall, which is the frictional component between the backfill and the wall, and also alpha. And so what that can let us do is then we can break these down into the horizontal component and the vertical component of that resultant. For our sum of forces and sum of moments calculation. So we're going to sum moments about the toe, for example. So we're going to see if this thing's going to want to tip over. And so it makes sense to consider doing it this way. So we'll see it presented like this in a lot of texts. In the end, our calculations are going to probably end up looking more like that. So a couple final details. What's phi wall? Here's a way to look that up. So there's different types of material on different types of with different types of soil. So last time we learned how to calculate the horizontal pressure. And this time we talked about some ways to include the possibility of an inclined backfill or a wall, or we can talk about friction on the back of the wall. And then we also started talking about forces, so a resultant value and where the resultant would land. And next time we're going to talk about our failure mechanisms. So one of them would be a retaining wall that wants to slide. And for this particular retaining wall, the way that we would analyze is figure out the gross weight of this section. And so we would have the weight of the soil, we would have the weight of the concrete, and we would have friction acting downwards on the back of the wall. This is our pressure distribution. We would also have a horizontal force from the soil, and then there would also be a frictional force at the bottom. And maybe if this material was embedded, there would also be a pressure distribution at the toe with a corresponding resultant. And we would sum all of these horizontal forces in the x direction, and we would look at the driving forces and the resisting forces, and we'll come up with a factor of safety based on that. The other failure mechanism with all of these same forces, so we've got a weight of soil, we've got a weight of concrete, we've got a frictional force that's acting on the back of the wall, and that's due to the soil failing. And then we've got a horizontal resultant. And what we would do is we would analyze this thing as a sum of moments about this toe. So we would have reaction arms for each of these, vertical forces, and we would also have a moment arm for the horizontal forces. And so we would sum those moments, we would come up with a factor of safety in overturning the resisting over the driving. So that's what we're going to do next time. So far we've covered a lot of theoretical ground, and next time it's going to be a big statics problem.